So welcome back everybody to the second of our two seminars for today. It's a huge pleasure to have Nathanaël Berestycki, who's going to be speaking about free boundary dimers, random walk representation and scaling limit. Over to you, Nat.
All right. Hi, everyone. Thank you very much, Christina and Alex, for the invitation. It's a pleasure to be here, if only virtually. I'll be telling you about some joint work that I've been doing with Martin Lis, who is now with me in Vienna, and Wei Chan, who is now in Paris, in Orsay. But this work started more than 3 years ago when we were all in Cambridge. And so hopefully we've reached the end and it will be on the archive soon. So here's the plan for the talk. It's, I think, a bit unusual because I will spend more than half of the talk, I think, talking about sort of classical stuff that is not our results, but I think is going to be interesting, hopefully, to many people, and is, I think, very beautiful. And then in the second half of the talk, I will tell you about what we have done, which is kind of particular case of the Dimer model where we change boundary conditions. I'll explain that. In some sense, the kind of plan for both parts of the talk, they look pretty similar. I'll talk about what is the height function and what is the Dirichlet Gaussian free field, and what is the random walk representation for the Dimer model. And you can see that the plan for the second half is, roughly speaking, the same, with the difference that Dirichlet has been replaced by Neumann. And here it looks like somehow the same tools are being used, but there's something really quite remarkable that I hope to tell you about, this random walk representation. There's some kind of miracle that we don't fully understand that I hope I will tell you about and will be interesting. All right, so let's start with the Dimer model. So we're going to take some finite graph, G, and G is, we're going to take it to be finite, planar, and bipartite, although it doesn't really need to be bipartite, but for some of what I'm going to say, it's important. So bipartite means that you can color the vertices black and white in such a way that two vertices of same color are not adjacent. So what is a Dimer cover? It's just a subset of the edges of the graph, which we call dimers, such that every vertex is incident to exactly one dimer. Okay, so here's an example of a Dimer configuration on a piece of the square lattice. And you can see on the picture on the right that there is an alternative way of thinking about it, where you've replaced the configuration of the Dimer configuration by a tiling of this portion of the square lattice by dominoes, so 2x1 rectangle. So what we've done is very simple. So we imagine that every vertex is at the center of a square, and if I've got a Dimer edge, I just glue the two adjacent squares, and that gives me a rectangle, 2x1 rectangle, so a domino. Okay, so these two pictures are obviously equivalent to one another. And what is a Dimer model when we have edge weights W on the graph? So here this is undirected. So for every edge, I give you a positive number WE. And the Dimer model is just the following. We pick one such Dimer covering M with a probability proportional to the weight, the product of the weight of the edges in your covering. And typically the situation we're interested in is the case where W is equal to 1. So this corresponds to selecting one of those Dimer configuration uniformly at random. Okay, so that's just a Dimer model. There is a fundamental tool for the Dimer model, a fundamental idea, which goes back to Thurston, and that's the idea of a height function. I'll give a definition, which is, I'll explain what that is in a second more precisely, but at least you can, in one particular case, this definition of height function is very visual, and I wanted to show this, this picture. So this is the case where you study a Dimer covering on the piece of the hexagonal lattice, the honeycomb lattice. And you can see that if we draw the analog picture in terms of tiling, what we have to do is we imagine that every vertex on the left is at the center, not of a square, but of a triangle now, an equilateral triangle. And again, if you glue two adjacent equilateral triangles, that gives you a losange. So these losanges are drawn here on the right, and they can be of three different possible orientation depending on the edges, the orientation of the dimer. So for instance, you have dimers like this are in correspondence with rhombi or losanges that are colored purple in this picture. In a different orientation, you have rhombi that are colored yellow, and the final orientation, vertical edges, are corresponding to turquoise or blue losanges in this picture. So, this is just a coloring of this tiling. But as you can see, as soon as you draw a picture like that, there is a way to interpret this picture by just viewing this set of lozenges now as a stack of cubes that you're seeing, as if there's a room somehow, and here's the corner of the room, and you have this stack of cubes on top of one another. And once you have this stack of cubes, you can define a notion of height, namely at every point I can ask myself, for instance, I can ask myself at this point, corresponds to this losange here, I can ask myself, what was the height here? What is the height, let's say, at the middle of this face? Where I measure the height, this is a bit, a matter of choice. I have to declare what is the height 0, and for me, I'm going to take it to be, let's say, this hyperplane here. Okay, and that's a bit of a choice of what is the reference frame. But once you have this reference frame, you can measure a notion of height. So at every point, again, what is the height of the stack of cubes that you see? And this notion of height allows you to encode the dimer model as a surface. So if the dimer covering is fixed, you're going to have a fixed surface representing the graph of this height function. Otherwise, if the dimer covering is selected at random, you're going to have a random surface. I'm going to give a more precise definition in a second, but I like this picture because it's very visual. Okay, so so here's a more precise definition. I spend a bit of time on this because I think it's one of the things that is the most studied about the dimer model is what does the height function look like. So one very nice way to do that is by superposing two dimer covers on top of one another. So here's one dimer cover on a piece of the square lattice, and here's another one on the right. And just like in the previous picture, you had a bit of a choice when you decided what's the reference frame to measure the height function. Here again, you have a bit of a choice, and the role of the frame is played by the second dimer configuration that you're considering. So this second dimer configuration could be fixed, deterministic. Maybe on the square lattice, you could have a sort of a boring dimer covering where all the edges are parallel to one another. Or the second dimer configuration could be random, in which case we call this model the double dimer model. So this is just the terminology that is used. So the choice of the second dimer covering is really equivalent to the choice of reference frame for the height function. In the end, this choice is not going to matter. It's not going to be relevant because we're going to subtract the expectation. So the choice of reference does not make a difference. Okay, so we have these two dimer coverings, and what we do is we superpose them. We just literally put them on top of one another. And what you see when you do that is basically just for deterministic reasons, there's two possibilities. Either there was a blue edge on top of a red edge, and so I call that a purple edge. And you can think of that as a double edge or maybe a degenerate loop of microscopic size. Or you have a red edge, which then alternate with a blue edge and red edge and so on and so forth. And eventually, just for deterministic reason, it has to be that these edges, they alternate from one another. And so they form loops. So this, you get a graph of degree 2, if you want, a subgraph of degree 2. And so this has to look like a gas of loops and double edges. So once you have this picture, how do you determine the height function? You're going to interpret these loops just as level lines for the height function. So we're going to start by imposing zero boundary condition everywhere on the outside. So it's 0 here, it's 0 here, it's 0 here, and 0 here. And then every time you move inside a loop, for instance, from here to here, the height can change, and it can change by plus or minus 1. The rules are written here. So basically, you have to imagine the following thing. So maybe let me put a bit of color. So we are on the square lattice. So the graph is bipartite. So I can have a coloring here, black and white, followed by black and white, and black and white, etc. And simply in order to determine whether what happens when you go inside a loop, how does the height change? There's really two possibilities. So blue and red are somewhat symmetric. So let's look at the case for a blue edge, like here. And then it depends whether you have a black vertex on your left or a white vertex on your left. In one case, you're going to declare that the height change is +1. And in the other case, you're going to declare that the height change is -1. And red is just totally symmetric. So for instance, as I go across here, I'm exactly in this situation. And so the height change is +1. Likewise, I could also go from here. You can see that this definition of height function is consistent. It's not very difficult to convince yourself. And so when I've done that, I've defined completely a height function everywhere. So the height is defined on the faces of the square lattice in this case. Okay, for each face, for each square, there's a well-defined value for what is the height. You can imagine, for instance, that this represents there's a map here. This is the ocean here. The height is 0, and this is an island. This loop is an island, and you ask yourself, well, in that island, what is the height? In that island, there can be mountains, there can be lake, and things like that. So, for instance, this is almost the same configuration. All I've changed is exchange the alternation of red and blue edges. It's the same. This loop is the same as before. Maybe I can show it again. The only thing that I've done is exchange the blue and red in this cycle. And so here, the height increased to 2, for instance. Okay, it increased from 0 to 1 across that edge and from 1 to 2 across that edge. Okay, so that's the definition of the height function. And so again, this height function has the property that when I superpose the 2 dimer coverings, the loops give me the level lines of the height function, basically. So this defines the height function. And the main question in the dimer model is what is the large scale behavior of this height function? So here are 2 pictures taken shamelessly from a work of Kenyon on the left and Kenyon Okunk of Sheffield on the right. And you can see that depending on the exact nature of the behavior of the domain near the boundary, some very different behaviors can occur. And so, for instance, on the right, what is happening is that the configuration of dimers in some macroscopic regions of the domain is completely frozen. So in this region, you will only see lozenges with a certain direction. Okay, so the direction is a certain direction here, another one here, another one there, and so on and so forth. And then there is a curve, a well-defined curve. This is called the Arctic curve, where inside that curve, the configuration of the dimer model, what you see appears much more random. This is called the temperate region or liquid region. This is called the frozen region, as I've said. And there is this very nice quote, which is taken from the paper of Kasteleyn, which I think more or less started this whole topic. And this quote says that the effect of boundary condition is, however, not entirely trivial and will be discussed in more detail in a subsequent paper. This is, I find that very amusing, from the perspective of roughly 50 years of research on this topic. yes, there's more than one subsequent paper to write about this. In some sense, what I'm going to tell you later on in the second half of the talk is about what happens when you change a bit the boundary condition of the domain, and we will see that very little is known in generality about the behavior of the height function. So what I will do is I will try to tell you a little bit about a remarkable, really wonderful result of Rick Kenyon about the Daimler model, which goes back 20 years now, a bit more than that. And in order to do that, I've got to introduce what is going to be the scaling limit for this height function. So this is the object that will, it's a continuous object, if you like, that describes what is the fluctuations of this height function when you send the mesh size to 0. And so what we do is we take a domain D in the plane with boundary. Yeah, okay. It's a bounded domain, I guess. And if I have this domain, I can introduce the green function in this domain. So what is it? It's simply, I take PTXY. So this is going to be the transition probability for a Brownian motion, the probability that it goes from X to Y in time t without leaving the domain D. So it's killed when it leaves the domain D. And so if I have this PTXY, what I can do is that I can integrate it between 0 and infinity. So if you want, it measures the expected amount of time that a Brownian motion would spend close to the point Y between time 0 and infinity up until the time that it's killed at the boundary. So what is the Gaussian free field with Dirichlet boundary condition or 0 boundary condition? This is written by Phi Dir in my slides. And this is a random distribution, meaning that the pointwise values are not well defined, but it's a random distribution such that when I integrate it against the test function f, I get a Gaussian value, and that Gaussian value has mean 0 and a variance which is given by this double integral. And that just means, if you want, that while the Gaussian free field is not a function, you can think of it as a function, and in that case, it is a Gaussian random function with mean 0 and the covariance given by the green function. This green function, okay, I'm missing a Dirichlet here on the top of the definition. Dirichlet because the Brownian motion is killed when it touches the boundary. So that's just the definition of the Gaussian free field. Again, the value is not defined pointwise, but it's well defined when we think of it as a random distribution. So there is a particular case where this green function has a particularly nice expression. And I mentioned this here because it will also play a role in the second half of the talk. So what is this case? So this is the case where the domain D is the upper half plane. I guess it's not bounded, but that's not so important. And what is the transition probability from X to Y for Brownian motion in the upper half plane killed when it touches the boundary? So there is this thing called the reflection principle, which I guess we learned when we learn about Brownian motion. But what does it say here? It says that I can, in order to go from X to Y without touching the boundary, it's enough, I can kind of sum over all trajectories that go from X to Y in the entire plane. So that's this term, but I've got to subtract those that end up in Y bar. Okay, so that's just the reflection principle. So the trajectories that end up in Y bar in the symmetric of Y are exactly, if you want, those that would have touched the boundary. So that's one way to think about it. And therefore, if you do the integration, if you start integrating between 0 and infinity this quantity, it suffices to understand what is the total integral of that thing, of just the full plane transition probability, if you like. And this is, okay, I'm cheating a little bit because it's infinite, this integral. But if it had a meaning, if it had a value, that value would be just up to a factor 1/2 pi. would be minus log of x minus y, the modulus of x minus y. And in fact, subtracting the term on the right is exactly what is needed in order to make this finite. And so when I do the integration, I get this term here for the integral of the full plane transition probabilities. And I get exactly another term of the same type, but where the sign has been changed because I've subtracted the trajectories that ended up in y bar. And so that's the value of the green function with Dirichlet boundary condition in the upper half plane. So what is Kenyon's really groundbreaking result, I think? So it was the first time that in probability and in statistical mechanics that there was a proof of conformal invariance for a model of statistical mechanics. So this was really a big deal when it came. And the result says that if you take a bounded domain, D, and you intersect it, you consider a fine mesh approximation. So D delta is just going to be essentially the intersection of D with a square lattice with mesh size delta, with possible modification on the boundary. So this is called Temperley boundary conditions, and I'd rather not get into the detail of what that means because it's a bit complicated. So appropriate boundary condition, you can think of it as just a fine mesh approximation of the domain D with appropriate boundary condition. You can then consider the dimer model on this graph. This is now a finite graph because the domain was bounded. And you look at the associated height function for this graph. The theorem says that if you look at the height function, you subtract the expectation, no further rescaling, then this converges to a multiple of the Gaussian free field with Dirichlet boundary condition as delta tends to 0. So this was really a fundamental result. As I said, it's the first time in statistical mechanics that there was a rigorous proof of conformal invariance. And the Gaussian free field has ended up playing a major role in many branches of probability over the last 20 years. But it's interesting to note that at the beginning, when Kenyon proved this result, I think it's fair to say that the object was not so well known. And in fact, he wrote 2 papers to do this, to prove this result. The first paper, he obtained limiting moments. I'll say a word about the proof in a second. He obtained limiting moments for this height function. And he observed that these limiting moments, they were conformal invariant. And so he said, okay, great, I've proved conformal invariance. And then later on, I think almost the same year, but obviously it's 2 separate papers, so they're very close in time. But he realized that actually these moments were Gaussian, were those of a Gaussian distribution. It's really non-trivial to check the Gaussianity. And these moments coincide with the Gaussian free field, with those of the Gaussian free field. And so he was able to identify this way the limiting distribution. But it's very interesting because, for instance, already in the first paper, he was able to say that the covariance of the field in the limit is given by the green function. And so nowadays, if you have a field whose limiting covariance is the Gaussian free field, that's really your first, if the limiting covariance is the green function, really your first guess will be that it must be the Gaussian free field. But back then, it was not so obvious. And so I think he was maybe the first to point out the importance of the Gaussian free field in statistical mechanics. So I'll say a few words about some ingredients of the proof. There is this remarkable theory developed by Kasteleyn really at the start of the subject that I'll explain, I hope. And then part of it is kind of to understand the boundary conditions, and that allows a computation of moments, which is at the end, as I said, where the result comes from. So let me say a word about Kasteleyn theory. Kasteleyn theory starts with a notion called Castellan orientation. So this is just, we are going to orient every edge. The graph was undirected to begin with, but now we're going to choose an orientation, and we're going to choose it with a very specific property. It looks a bit strange at the beginning, but the property is that if you pick any face, for instance, this face, and you go in some direction, you only encounter an odd number of edges that go in the opposite direction. So for instance, here I'm going in this direction. What are the edges that go against me? There's this one, there is this one, and there is this one. So there's 3 edges that go in the opposite direction. Maybe I should leave something so that you can see. So the 3 edges that go against me are this one, and this one. So this is odd. 3 is odd, so it satisfies the property. If I take another face, for instance, I don't know, maybe this one, then what are the edges that go against me? Well, there is this one, and that's it. Okay, so this is also 1. 1 is also an odd number. So it is a Castellan orientation. You can check it for every face. So what is the principle of this orientation? How is it defined? It's defined by saying that if I look at the vertical edges, they all have the same orientation. They're all going down. And the horizontal edges, they just alternate between going left and going right. Oops. Okay, you understand what I'm trying to do here. They just alternate. And so that's how it's defined. So that's a Castellan orientation. At first, as I said, it looks like a slightly strange definition. Now, what is the key object is the Castellan matrix. So what is a Castellan matrix? So I have a graph. Associated to this graph is an adjacency matrix. And the Castellan matrix is basically the adjacency matrix of this graph, except that I incorporate the signs as well, the signs coming from the Castellan orientation. So in particular, this matrix is going to be anti-symmetric. So just to clarify, the entry associated with this pair of vertices, so if this is x and this is y, then kxy will be 1, but kyx will be -1. Okay, so that's just that. That's just what the Castellan matrix is. It's a signed adjacency matrix where the sign comes from the Castellan orientation. And the remarkable theorem of Castellan, which was proved simultaneously, I think in slightly less generality, but basically it's the same result, by Temperley and Fisher in 61, says that Z, okay, I did not define Z. Z is, okay, I did define it actually. It's a partition function of the model, meaning you can think the total number of dimer configuration when the edge weights are constant equal to 1. So in the uniform case, the number of dimer configuration is counted by the absolute value of a number called the Pfaffian of the matrix K. The Pfaffian is a variant of the determinant. I'm not going to define it, but I'll say a word about where the result comes from. And in particular, something which is even more crucial is that if I'm interested in computing the endpoint function of the model, so the probability that this edge is in the dimer, that edge in the dimer, etc., etc., it's given by the Pfaffian of the matrix K inverse. And so if you're given this fact that the total number of dimer configuration is given by the Pfaffian of the matrix K, the fact that the correlation are given by the Pfaffian of K inverse is an elementary thing in algebra, in linear algebra. Essentially, it comes from, so think in terms of determinant rather than Pfaffian. It's essentially the same thing. It's essentially the way you compute the inverse of a matrix using determinants of the co-matrix. So this is, I think, Kramer's rule from linear algebra, except of course, you know, to make the link with linear algebra, it requires to recognize that this is what it is. It takes a bit of thought, but you know, this is really what it boils down to. So I'll say a few words about where this formula comes from. It's really the starting point, and it's a crucial thing about the dimer model. This is why it's possible to say so many things about it. So yeah, so where does the formula come from? Where does this theorem come from? Well, one way to see it is instead of showing that Z is equal to the absolute value of the Pfaffian, what you can do is you can square this identity. So let's show that Z squared is equal to the Pfaffian squared. Now it turns out I've not defined the Pfaffian square, but actually that is, I've not defined the Pfaffian, but it turns out one way to define the Pfaffian is such that the Pfaffian square is the determinant. So in fact, what we have to show is that z squared is equal to the determinant of k. Now, why is this true? So let's think about what does determinant of k looks like. You know, we can write down a sum of a permutation with a sign of the permutation. And because k is an adjacency matrix, the only permutation that will contribute to this sum are such that, well, they look like cycles, basically, okay? So that's because k is an adjacency matrix. So k is 0 as soon as you try to go, I don't know, from here to here. So the only permutation that matter are those that can be written down as cycles that you can draw on a graph. Okay. And furthermore, this strange choice of the Castellan orientation is designed so that, in fact, the sign of the corresponding permutation is constant. And altogether, it gives you 1. And so that means that we are writing down the determinant of k as kind of all the ways to assign, that's just equal to the number of ways to assign loops and double edges to this graph. And as I've said, that's one way to think about the dimer model, the double dimer model. So indeed, when we write down determinant of k, we've obtained 2 configurations of the dimer model, and therefore that's equal to z squared. Okay, so that's in a nutshell the proof of Castellan's theorem. And as I said, the main consequence for us is that if you try to say something about the dimer model, what you need to understand are the correlations of the edges, and therefore what you need to understand is the matrix K inverse in the limit of large scale. So this is the inverse Castellan matrix. The problem is to compute the inverse Castellan matrix when the graph becomes very large, if you like. In order to do that, Kenyon had really a remarkable idea. And the idea, so he didn't call it a random walk representation, but I will call it that because I think that's what it is. And his idea was to not think so much about the matrix K, but the matrix K star K. So K star here is going to be the Hermitian conjugate of K. And the idea is to think about this matrix. Let's call it L. L because in a second it will be, we will see that it's really a Laplacian. And what does this matrix do? So we can sort of do it visually somehow. Okay, so first of all, this really is matrix multiplication. So if I think about the entry associated, what is, for instance, L of XX, and this is X. Okay, here's X. So how am I going to compute it? Well, you know, it's matrix multiplication. So I've got to sum over all possible points. Okay, so this is going to be the sum over Z of K star XZ, and then times KZX. That's just matrix multiplication. And because of that, you know, K again is just has non-zero entry on nearest neighbors. So it counts, if you want, all the ways to come back to X in 2 steps. Okay, so I can go from X to X this way, and then that way, and then that way, and then that way. Because of that, the entry will be -4, actually. So there's a sign as well, and the sign is -4. And you can see that L has, you know, it's not because, you know, I'm taking 2 steps at once when I do this matrix multiplication. It's impossible to get non-zero entries. It's impossible to get something not, let me try to say it correctly. In order to get something non-zero, the only way to do it is to have a white vertex evaluated with a white vertex, or a black vertex evaluated with a black vertex. There's no way to go from white to black in 2 steps, okay? So first of all, it splits this matrix into acting on white vertices and acting on black vertices, if you like. And in fact, you realize that if I try to go from here to here, there's 2 ways you can go. You can go this way or you can go that way. And it just so happens that the contributions, they just vanish. So in fact, you can split further your lattices, the white lattice into 2 and the black lattice into 2. There's white 0 and white 1. There's black 0 and black 1. And you realize that once you've done that, L becomes just the discrete Laplacian operator on each of these 4 sublattices with appropriate boundary conditions. And that's why Kenyon had to come up with a specific boundary condition that we now call Temperleyan. But, you know, Laplacian is a very good object. We understand it very well. We know that it has something to do in the scaling limit with Brownian motion. And it's not surprising that as a result, we can say something about K inverse. And the idea is to say, well, in terms of L, so we have L was defined, I remind you, as K star K. I obtain K inverse simply by multiplying by K inverse in this relation. And I have that K inverse is the Laplacian inverse multiplied by K star. Now, the inverse of the Laplacian is basically nothing else but the green function, the discrete green function. And K star is essentially nothing else but a discrete derivative. And so this formula, if you want, tells you that in the scaling limit, the matrix K inverse corresponds to the well, not discrete, but really the continuum derivative of the continuum green function. So from this, it's a very long computation. The paper is long and very hard to follow, but we can understand K inverse in a large scale. And so Castellan theory tells you what is the scaling limit for the endpoint correlation function, and therefore that's how you get in the limit, the scaling limit being the discrete, the continuum Gaussian free field. Okay, so this is a summary of what Kenyon did and Castellan theory. And what I'm going to do now is tell you about our work, which is about a modification of the Daimer model, which actually we've not agreed on a name for it, although we weren't the one who introduced it. I like to call it the free boundary Daimer model, but my co-authors prefer boundary monomer Daimer model. So I'm not sure. You feel free to vote and tell me what you like best. So I will tell you what that model is. It's a very simple modification. So simply, what we're going to have now is we're going to have a part of the boundary called partial M, where vertices are allowed not to be part of the dimers. They're allowed to remain isolated because they're allowed not to join a dimer. They form, in that case, what we call a monomer. Okay, so, and they're just, these vertices are just allowed on some specific part of the boundary, which you choose. Okay, that's part of the choice of the model. So again, a monomer dimer cover M is just a set of vertices and edges such that, so the edges you're going to call dimer and the vertices you're going to call monomer, and such that each vertex is covered exactly either by a dimer, exactly once, either by a dimer or by a monomer. Okay, so that's what we want to call a monomer dimer cover or a free boundary cover, up to you. And then the model that we want to study is the same as before. So we pick such a configuration with probability proportional to the product of the edge weights in your dimer cover, and you also get a different weight for each monomer, so ZV. So the model we're going to focus on, just for simplicity, will be the case as before, where the edge weights for the dimer is 1, and each monomer contributes a weight Z. Okay, so another way to put it is that the probability of a configuration is just Z to the number of monomers in your configuration. And obviously, yeah, I don't want to try and justify the model too much, but you can, if you want, think of them as impurities in the medium. So okay, so here on the left is such a dimer configuration, such a monomer dimer configuration. You see that some vertices at the bottom. So for me, you know, this is going to be the typical situation that we're going to be doing things in the upper half plane, and the part of the boundary where, oops, what is going on here? Can you still see my screen? Okay. Well,
all looks fine to us.
You've lost it?
No, all looks fine for us.
Okay. For me, it says that my screen sharing is paused. I don't know why.
Maybe it's paused. Can you press resume sharing?
How do I do
if you can get the control bar to come up, then there should be an option to resume sharing.
I think I will just redo it again. Sorry, I will just
Sure.
stop the share and restart the share. How about that? Sometimes this is what happens. No. 1 second, excuse me. Okay. Okay, it looks like we're back.
Perfect.
So you see that some vertices here, indeed, they are not part of a dimer, and that's because for me, the part of the boundary that I don't want to allow, I want to allow monomers is just going to be the real line. Okay. When you have this free boundary dimer or monomer dimer, however you like to call it, you can do essentially the same game as before. You can define a height function, and the difference is simply that the height on the boundary is not going to be constrained to be equal to 0. And it can take pretty much any value you like. So let me show you how that works. So if you superpose two such configuration, one on top of the other, you get the same thing as before. So some edges are going to be double, and some will give you cycle. The thing that's different is that you can also get some boundary arcs, so places that join curves that go from the boundary to the boundary, to the monomer part of the boundary, to the monomer part of the boundary. So yeah, we have a conjecture about the scaling limit of these arcs, but I'm not going to tell you about it, I think.
Do you worry about places which have got two monomers versus places which have got a single monomer, or is that just...
No, I guess you can imagine this is, there is a macroscopic boundary arc connecting them that you don't see somehow. You could, yeah, that could happen. Okay. So, but you can, so in principle, you know, you can do exactly the same thing as before. It still makes sense to talk about the height function. It's just that the height here is unspecified, and you need to approach, you know, points to figure out what is the height function just from other sides. You cannot do it from here because here there's no constraint on the height. It doesn't have to be 0. But for the same reason as before, it is well defined. Okay, so there is a consistent choice. So there's no problem. Okay, defining the height function. Now, if I want to guess what is the scaling limit of the height function, here's what turns out to be actually a somewhat misleading argument, but you won't see that at the moment. One way to do that is to think about taking your free boundary dimer configuration and just reflecting it. So I just I add a line somehow at distance a half from the monomer part of the boundary, and then I just reflect this entire configuration. And you see that in this way, you know, I get I get dimers in a domain that's twice as big, but also with monomers that are sitting across from one another. And so what I could do is I could pretend that these monomers, they are joined by an edge. And then when I have that, okay, it doesn't say that. When I have that, I've just got a dimer configuration really living in this entire domain, double domain. And the only thing that's special about this dimer configuration is that the height function is conditioned to be even. So the value of the height here will be equal to the value of the height there. I wonder, there was a question?
There's a question in the chat.
Can you see? I don't see it. I just saw.
I can read it to you. So can you allow monomers in the interior?
Yes, so very good question. Certainly, there's nothing that prevents you from allowing a monomer in the interior. In fact, this is a topic of a famous conjecture. But what you do lose with allowing monomers in the interior is the notion of a height function. Okay, so that's important. If you want a height function, you need to allow only monomers on the boundary. This is why I don't like so much the name monomer dimer model, because really the topic of the famous conjecture is when you can have monomers really in the interior. So we are just allowing monomers on the boundary. It's hard enough. It's just, if you want, you can think of it really just about, I prefer the term free boundary condition for dimer model, because that's really what it is, what we're doing.
And then
Okay.
there's another question just while you're there. Is there a free boundary variational principle for limit shapes? Asks Istvan.
Is there? Wow. Okay. So this is okay. So this is a very knowledgeable question. The question is whether there is a variational principle that describes kind of the limiting behavior of the height function, but not the fluctuation at the level of the large numbers that you can compute in terms of a variational principle. Yeah, that's a great question. Really very good question. I don't know. If you know about these things, okay, maybe ask me again in the question. I'll tell you.
I'll ask you at the end.
Yes, I'll tell you some interesting things one can think about. Okay, so it turns out that if you want to condition, so we have this height function that is conditioned to be even, and it turns out that in the continuum, it makes sense to condition the Gaussian free field in the full plane to be even. And this is really what the Neumann Gaussian free field is. You can think of it as the even part of a Gaussian free field in the entire plane. And another way to define it, to describe it, is to say that you're now going to consider the green function of Brownian motion, but not killed at the boundary. Instead, it's reflected on the boundary of the domain. And again, in the upper half plane, something special happens that you can compute it exactly. And that's if I want to find the probability to go from x to y in time t while allowing reflection, okay, so I allow myself to come here and be reflected at the boundary, then one way to do that is to go from x to y in a full plane, or to go from x to y bar in the full plane. So now, instead of subtracting trajectories that ended up in y bar, I just add them up. Okay, and this is something we're going to see even at the discrete level in our model. So this is why I mentioned it, because I hope to say at the very end that we see something like that exactly at the discrete level in our model. So yeah, so there's an extra term that accounts for trajectories that went through the boundary somehow. That's where it is. And that leads you to an explicit formula for the green function with Neumann boundary condition. So here's the content of our main result. The first result says the following. So we take, first of all, an approximation of the upper half plane by bigger and bigger domains. So here's the real line, and here's the domain dn. That becomes bigger and bigger in such a way that, eventually it becomes the upper half plane. And the real line is where I'm going to allow monomers. So the first part of the result says that as n tends to infinity, the infinite volume limits of this random monomer dimer configuration exists. It's not trivial. There's no monotonicity, no. In fact, it's a very technical part of the paper that allows us to say that. But then, okay, so, and then the second part of the result says, consider the random monomer dimer model in the entire upper half plane, and then send the mesh size to 0. The result says that in the scaling limit, the height function minus its expectation converge to now a Gaussian free field with Neumann boundary conditions as delta tends to 0. Yeah, so maybe a couple of comments. So first of all, this is a result that's true for any z, and maybe this is a bit surprising. So I remind you that z is a weight that you get for every monomer in the model. So there's kind of two boundary cases you can think about. So maybe z is equal to 0 and z is equal to infinity. So when z is equal to 0, nobody wants to be a monomer. And so it's just the usual dimer model in the upper half plane. Okay, and then the height function we know from Kenyon's result that it converges to a Dirichlet Gaussian free field. So that's the first boundary case. The second boundary case is when z is equal to infinity. In that case, everybody wants to be a monomer. And so effectively, the model reduces to the usual dimer model, but with one row less. Okay, you've got the entire real line has just monomers everywhere, but it's kind of boring. And so you get just the dimer model, but you've removed this bottom row of monomers. It's still the upper half plane, obviously. And so again, the height function will be given by a Dirichlet Gaussian free field. So you've got these two boundary cases, z equals 0, z equals infinity, where the height function looks like a Dirichlet Gaussian free field, and yet everywhere in between it's something else. It's a Neumann Gaussian free field. And yeah, I should say that this is really the first time, I mean, the Neumann Gaussian free field is a very important object. It shows up in a lot of unrelated stories, for instance, in Liouville quantum gravity. It's very important. But it's the first time that there is a discrete model where the limit is shown to, in fact, to be something else than the Dirichlet Gaussian free field. Okay, so that's the main result. Are there questions on the result, on the statement, at least? Okay, feel free to interrupt us, obviously. So let me give you a very short sketch of a proof. And the beginning is a very nice idea. It's in a paper by Giuliani, Josselin, and Elliott Lieb from 2015, which shows that there is a bijection between the monomer dimer model and a dimer model, but on an extended graph. And this extended graph, what you do is you just add triangles everywhere on the part of the boundary where you would have allowed monomers. Okay, and instead of monomers, there's going to be dimers living on this graph. The trouble with this graph is that it's non-bipartite because we've added triangles, but so that complicates a bit the story, but it's still a very nice observation. Actually, something quite amusing about this bijection is that the authors state in their paper that this bijection was suggested to them by the referee. So in the end, we don't know who is the author of this very nice bijection. So their paper proves a Pfaffian formula for the correlation in the monomer dimer model, but the referee said, look, it's basically trivial because of this bijection, and then you just apply standard Castellan theory. So this is a very nice observation, but we don't know who made it. At least somebody knows, but I don't know who it is. Yeah, so it's just that. So what you do is that instead of having a monomer, you try to replace monomers by edges from the triangle. And okay, so, and then, you know, if a vertex here does not have a monomer, for instance, this one is part of a dimer, well, you're just going to use that edge as a dimer edge. Okay, so to not break the constraint that it should still be a dimer covering. So this vertex should still be covered by something. And one can check this really works. So this really is a bijection. There's only one way to do that. So you can go from left to right, or you can go from right to left. So for instance, if you start here, then this, you know, this edge needs to be there, because otherwise this vertex is not going to be covered. And you can go from left to right, and you can go from right to left. You can check these things agree. There's really one way to do that. Right, so we've got this graph. We've got a dimer on the strange graph. It's the square lattice, but to this we've added some triangles at the bottom, and that makes things a bit complicated. So first of all, you can come up with a Castellan orientation. It's basically the same as before. So the vertical edges are still going down, including the kind of edges of the triangle where things are going down. And then horizontal edges, it's still the same rule as before. And you know, it alternates between going from left to right. And that's really, in some sense, the same orientation as before. And because of that, it's still a Castellan orientation. Particularly, if you can check, if I go in this, I will find here this one edge going against the flow. So it's still a Castellan orientation. Now, what is the issue? You think, okay, great, you know, this seems like a good place to start the same sort of things that Kenyon did. And you try to think about the Castellan matrix and the associated matrix L, which is K star K. I should probably write this, it's still the same definition. The trouble is that near the bottom row, the row where you have monomers, like everything goes wrong. And the problem why everything goes wrong is that the signs are just totally messed up. There's nothing that's there's no, like, if you look at the diagonal values, the entries of this matrix on the diagonal, they're not at all equal to the sum of the off diagonal entries as it should be for Laplacian. like everything is wrong. Okay, so you can still, look at a matrix pxy, which is, it ought to be a transition probability for a random walk. This is what it is in Kenyon's case. It's a transition matrix for just simple random walk on each of the 4 sublattices. But in this case, it's not at all. It can be signed. It doesn't sum up to 1. So it's they are transition matrix, but with negative probabilities and not summing to 1, which is bad news for probability theory. But that's somehow our only tool. We need to understand K inverse, and so we need to understand L inverse. So the question is, can you still make sense of the inverse of the Laplacian for transition matrix that are signed, that are like that? That's kind of the question. And so this is where something which I think is really a miracle happens. And that's, it's, of course, there's no way to do it in principle, but something very special happens here. And this is, maybe I need to go back to a picture. This is what happens. This miracle happens when you try to say what would be the probability to go from one place to another. I don't specify, what I do. I allow the walk to have as many steps as it like. It can do a big excursion in the monomer row, and at some point it's going to come back. Okay, so it starts here, the walk, it does a bunch of stuff in the monomer row, and at some point it comes back up. And I ask myself, what's the probability that I would do that? And in principle, this probability, as I said, it can be signed, it doesn't sum to 1 or whatever. So the thing that happens is that when you group all these walks together, you sum over paths that go from one place to another just by having excursions into the boundary, into the real line, if you like. Then you end up with weights that's positive and sums up to 1. So there is an effective random walk without any killing that describes this matrix K, that describes this matrix L rather, K star K. Simply, you've got to group together all these walks that spend time in the bottom row, in the lowest row of the graph, and you don't care what these walks do so long as they come back at the place that you asked. Okay, they come back out exactly at the place that you asked. And so, if you want, this now defines a matrix, everywhere in the upper half plane, except you don't have, you're not allowed to talk about the values on the lowest row. And when you do that and you kind of group the walks in this way, you've got something that is positive and sums up to 1. And it really, there's something quite miraculous that happens here. We don't really understand, we don't have a conceptual proof of why that is. It's just a computation, a very complicated computation, but that's what it is. And yeah, it's kind of an open question to understand where that comes from, this random walk representation. So I'm out of time, so I will just finish in 1 minute maybe. And just to say where the scaling limit comes from once you have that. Well, so we can still apply Castellan theory. We've got L inverse, and the point is that we now understand L inverse a little bit. It's got to do with the green function of this effective walk. And this effective walk, it can now jump along the boundary, but somehow it has a property that jumps, they are not too big. So the probability to make a jump of size K has a tail that you can compute, and it's exponentially decaying with K. And so the scaling limit of this walk is going to be given by reflecting Brownian motion. So already it starts to sound a bit like Gaussian free field with Neumann boundary condition. And in fact, at the technical level, concretely, when you try to compute the endpoint correlation of the model, so for instance, here, this is a 2-point correlation. So Castellan theory tells you that it's given by a Pfaffian of a certain matrix. And when you write it out, you get a bunch of terms. And compared to Kenyon's work, the only difference is that there are now these terms that include things that normally would be 0 in Kenyon, simply because for Kenyon, it's just not possible to for the walk to go from a white to a black vertex. But for us, it is actually possible to go from a white to a black vertex. except that if you want to go from a white to a black vertex, you know you've got to go through the boundary. That's the only way you're going to exchange lattice. And so, you know, this is exactly sort of the analog of the property that I was mentioning for the continuum green function with Neumann boundary condition. So you've got this extra term that accounts for walks that go through the boundary. And if you do the computation is long and complicated. It mirrors in some ways that of Kenyon, but it's also different in other ways. But still, at the end, you get the right scaling limit. So that's it. Basically, that's where I wanted to stop. And thank you for your attention.
Thank you very much. So I'd like to invite people to ask questions. I think we've got one still to deal with from the chat, but perhaps I can ask something much more fundamental or much more basic before we get to that, which is just I'm trying to make sure that I understand your random walk representation. So I'm just performing simple random walk in the interior, but whenever I hit the boundary, I'm then sort of teleporting somewhere. Is that right?
That's right. Yeah.
Okay.
Yeah. And in principle, it could go as far as you like. It's just that if you want to come out very far, then the corresponding weight associated with such a transition is tiny.
Is exponentially small in distance or something.
You know, where the weight accounts for the sum over all paths, so there's a ton of cancellations that takes place. And it's kind of miraculous.
Thank you. So so perhaps let's deal with the earlier question first. So if I can just find it. So
I think it had to do with the...
Is there a free boundary variational principle for limit shapes? That was the question.
Right. So the short answer is I don't know. There are a number of things you might like to test. So there are, you know, before you can do limit shape, variational principle and limit shape and things like that. I think this is where the question is trying to ask is, what are the phase diagram? Do you have frozen phases? Do you have liquid region, etc.? So this is predicted by the variational principle. And before you do a variational principle, in the case of the Dimer model, what people did was to study the question for one very concrete domain, which is the Aztec diamond, which I badly attempted to draw right now, and thankfully it's erased. So you could, I think a good starting point for this would be to try to look at the Aztec diamond as a domain, but allow half of the boundary to be free, to have monomers. And I think what I would expect is that in a situation like that, the limit shape will be given by the minimizer of the standard variational principle, the one proved by Kenyon and Kohn and Prop 25 years ago, I think now, for the regular Dimer model, but without a boundary condition. So, you know, there's, let's say you have a Dimer here and monomers there, then I guess the boundary condition will be 0 here and no specified boundary condition over there. And I think this is what will happen, but I don't know. In particular, this should predict what is the frozen region and what is a temperate region, what is a liquid region. But okay, I don't know. So this is the short answer is I don't know. It's just that I think this is what might happen.
Istvan, is that okay? Feel free to unmute if you would like to ask further. Oh, okay.
Yeah, thanks. Yeah. Other possibility would be somehow maybe mix the Dirichlet-Neumann boundary conditions, or
right.
If that makes
exactly. Yeah, that's maybe it amounts to the same thing actually. So it might be, you know, Dirichlet here and Neumann there. For the Gaussian free field, somehow it makes no difference whether you call it free or whether you insist on having really Neumann boundary conditions, so 0 normal derivative. It ends up being exactly the same object for the Gaussian free field, so maybe also for the solution of the variational principle. I don't know. Maybe.
Yes, thank you.
Yeah.
And then there's a question from Lorenzo. Lorenzo, would you like to unmute yourself and ask your question? Or if not, I can do it.
Yeah, so I know that in the Dimer case, one can count the number of configurations as the square root of the permanent of the adjacency matrix of the graph, so without choosing any orientation. And then in the case of a two-dimensional lattice, you can actually evaluate this permanent as a determinant of a related matrix.
Right. Exactly. So because the permanent would be the same thing as a determinant when you include the Castellan sign, right? That's exactly what's happening.
Yeah. So I wonder if this can also help in the monomer dimer case.
So I would imagine that's the case, because if you take the unsigned adjacency matrix of the graph, you know, the one with the triangles, then its permanence should count the number of monomer dimer configuration. I would guess. I mean, I'm not sure, but I think that's.
Mm-hmm. So maybe one could try to then evaluate this permanent. Yeah,
the problem is that the permanent is a much harder quantity to evaluate or to compute than the determinant, right? It's usually determinants are nicer than permanents, and this is certainly the integrability for the dimer model. You get it from the determinantal side.
Mm-hmm. Okay, thank you.
I mean, at least I don't know, but you know, I'm not. It's not really my area of specialty. So I'm not aware myself of a result where you can compute things efficiently by thinking of the unsigned adjacency matrix and trying to look at the permanence of the adjacency matrix.
Thank you very much.
Yeah.
Does anybody else have any other questions? I can't see anything else in the chat. Okay, in that case, I'm going to